Hi, welcome to our pre-calculus. The topic today is finding solutions in an interval for a trigonometric equation involving a squared function. Problem type 1. So here's an example. Secant square of theta minus 2 is equal to 0. So here we are seeing for the first time square of a trig function. Let's go and just review some basic algebra before we get started. So suppose I have an equation of the form a squared minus b squared equal to 0. What can I conclude from that? Well, I can factor this a minus b times a plus b equal to 0, and from the zero factor theorem we had last time, either the first parenthesis is 0 or the second parenthesis is 0, which gives a either is equal to b or a is equal to minus b. So either of these two possibilities have to be considered. Sometimes you approach this problem in a different style. You write it as a squared is equal to b squared, and then you say let's take square root. When you take square root, plus or minus is born in that operation, that a could have been b itself or a could have been the negative of b. A is equal to plus or minus b means the same thing that is written here, that is either a is b or a is minus b. So let's go ahead and apply this approach to several examples that we have here. So secant square of theta is equal to 2. So if I can take square root, right hand side is plus or minus square root of 2. So I can go ahead and take the reciprocal of both sides. Secant is 1 over cosine. 1 over cosine is plus or minus square root of 2. So cosine of theta is 1 over either plus or minus square root of 2. Simplify that a bit further or rationalize, you get plus or minus radical 2 over 2. Let's separate this thing into two groups. If you say cosine of theta is radical 2 over 2, or if you say cosine of theta is minus radical 2 over 2. Again, this is something that you can go and investigate with the pictures that we were drawing, or with your unit circle or a table. You want to try a variety of things and make sure all of your answers agree with each other. So let's go to my favorite unit circle. This was, you remember, was cosine axis. If you have a value for cosine, you draw it here. You draw a vertical line, connect to the origin, and these are the two angles that you want. Since we want between 0 and 2 pi, here we get these two. So theta becomes pi over 4, and pi over 4 short of a full circle, which is 7 pi over 4. For the second one, minus radical 2 over 2, we draw the picture, the vertical line at this would be minus radical 2 over 2, and the two angles that we are after will be this one and this one. So in that case, our angles will be 3 pi over 4 and pi over 4 after pi, which will be 5 pi over 4. Putting them all in a list, we get pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. All of the angles at these four corners become our targets. Okay, all the problems in this section the same style. Again, if you wanted to, you could have looked up cosine of cosine goes with x, is that right? Cosine is, we want it to be radical 2 over 2 or minus radical 2 over 2. All of these things are going to give us our answers. We draw these pictures every time to just remind ourselves where sine and cosines happen to be. Another example, we have 4 sine squared minus 3 is equal to 0. So this becomes 4 sine square of theta is equal to 3. You can take square root or first divide and then take square root. Sine square theta becomes 3 over 4. We take square root of this thing, sine of theta becomes plus or minus radical 3 over 2. So radical 3 over 2, again, we draw the unit circle. Remember, vertical is for the sine. Radical 3 over 2 is somewhere here. We draw horizontal line here and then connect to the origin. The two angles you see are what we are after. So if you say sine of theta is plus radical 3 over 2, we learn that the answers in that case are pi third and 2 pi third. If you say sine of theta is minus radical 3 over 2, minus will be here, minus radical 3 over 2, and you draw your line in that place, and here are the two angles you're after, and to make it stand out, here's one of them and here's the other one. So what do we list here? We say theta 4 pi third, and then the other one will be 5 pi third. So all told, pi third, 2 pi third, 4 pi third, 5 pi third. These are the angles from 0 to 2 pi. It would have been like the vertices of a hexagon, except that these two are missing from it. Those other 4 are included, and that's our answer. Same with every one of them. So this one says 3 cosecant square of x minus 4 is equal to 0. So that means cosecant square of x is equal to 4 over 3. So cosecant of x is plus or minus 2 over radical 3. So cosecant is same as 1 over sine. So 1 over sine is plus or minus 2 over radical 3. So take the reciprocal of both sides, and then this becomes plus or minus radical 3 over 2, which is exactly what you had over here. So same answers apply. Your angles are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So I don't repeat that, we just did that. Cosine square of x minus 1 equal to 0. So that means cosine square of x is equal to 1, which means cosine of x is plus or minus 1. If you try cosine of x is equal to 1, you get x is equal to 0. So how do we see that there's only one answer here? Cosine of x, so this is for the cosine axis. So I go as far as 1 here and draw my vertical, or the vertical just strikes the circle just at that starting point. There normally we would have said 2 pi 2, but 2 pi is excluded from the list of angles. We go starting from 0 short of 2 pi, so we stop there. If we say cosine of x is equal to minus 1, we are looking at this one. This is minus 1. At minus 1 we get x is equal to pi. There are two answers that they become they merge each other, and so that just pi survives. So our answer in this case is just 0 and pi, instead of these other solutions where we have 4 roots. Here we have 2, but in some sense each of them count twice. Tangent of x, tangent square of x is equal to 1. So tangent of x is plus or minus 1. If you stay with tangent of x is equal to 1, let's draw this picture too. We said for tangent we draw our tangent axis here. Here's 1, you connect to the origin, and you are looking for these two angles. So x is equal to pi over 4 and 5 pi over 4. If you say tangent of x could have been minus 1, minus 1 is here, you connect to the origin, and the two angles that you are looking for there are going to this location and the other one coming all the way around, and our answers become 3 pi over 4 and 7 pi over 4, and then the list of all of them. Do we have more? Well, just one. Cotangent of x, cotangent square of x is equal to 3. So cotangent of x is equal to radical 3 plus or minus. Cotangent is same as 1 over tangent of x. So tangent of x, take the reciprocal of this, becomes 1 over radical 3. Rationalize radical 3 over 3. So if we say tangent of x was radical 3 over 3, x would have been pi 6, pi 6 and 7 pi 6. Here's a picture for it. So radical 3 over 3 is about 0.6 or something. We connect. These are the two angles we want. What's the famous angle that matches this thing is pi 6. The other one is pi plus pi 6, which is 7 pi 6. If you say tangent of x is minus radical 3 over 3, x becomes, so here is the minus case. We go from here to the origin to the other side. The two angles you are after now, one goes here and the other one comes all the way. So again, you look up at your table and then you see 5 pi 6 and pi 6. So this is pi 6 short of 2 pi. How do I remember? So 2 pi minus pi 6. Take common denominators, 12 pi minus pi, and I get 11 pi over 6. So that's how I am working these things out. How you want to do it. Again, you have table, you have pictures, and you have the circle. Pick something, and 5 pi 6, 7 pi 6, 11 pi 6. Okay, so what did we learn in this section? If the equation is cast in the form of so-called perfect squares, something squared minus something else squared equal to 0. What are the solutions? We take it to the two sides of equation, we take it to the two sides of the equation and take square root, allocating plus or minus to one side of this. Then we track two possible cases, so each of them give their birth to its own roots. And then we collect all of them, and then that's when we're all done. Okay, until next time, good luck and God bless.